Hello, this is a tutorial on how to work on experiment number 9 in Chem 152. In this particular tutorial, I'm going to do 4 examples in which I will first determine the Lewis structure, then come up with the molecular geometry, use the internet to get the three-dimensional structure and find the dipole for these chemicals, and then paste the illustration into the worksheet. So the example that we will be doing today is these chemicals, CH2F. This is difluoromethane. Another one is HOCCOH, and this is ethane. 1,2-diol. Then we're going to do HCCH. This is ethine or acetylene. That's a common word. That's a common name, I mean. And then we'll do acetic acid. In this particular tutorial, we'll work with first determine the Lewis structure. From the Lewis structure, we'll get the electronic and the geometric designation. And that is via the valence shell electron pair repulsion theory. And then from the geometric structure, we'll determine the polarity. Using this information, we're going to use Molview and ChemEd DL to look up some properties in the internet. So the chart that we're going to be using is this. This is the chart we're going to fill out. So the first structure I said was CH2F2. Then we have HOCCOH. And then we have HCCH. And then finally we have acetic acid, CH3COOH. We're going to determine the total valence electron. We're going to draw the Lewis structure. We're going to determine the electron group and the geometric group, and then we'll finally finish with 3D structure and the polarity. The tools we're going to use is this VSEPR table right here, and this will tell me what type of geometry, the electronic geometry right here, as well as the molecular geometry. And the first chemical is difluoromethane. And the formula is CH2F. This is a neutral compound, CH2F2. And the way I teach my class is through what I call a bond table. A bond table simply tells me how many bonds the structure contains and how many lone pairs. Now, you could probably do this through trial and error by inspection, but I want to show you a systematic way of going about it so that you will always get the true answer. And remember that this technique only works when your chemical obeys the octet rule. So in this corner we write the formula CH2F, then we determine the number of atoms, 1 carbon, 2 fluorine, and 2 hydrogens. Then we have 2 columns. One's called OE. This stands for octet electrons. And then the other is TVE. This stands for total valence electrons. The octet electrons are the number of electrons that an atom would contain if it had the same number of electrons in its valence shell as the closest noble gas. And so carbon, that would be 8. So 1 times 8 equals 8. Fluorine, that also would be 8. So 1 times 8 equals 8. On the other hand, hydrogen is satisfied with 2. It's called the duet rule. So we say there's 2 hydrogens times 2, and that's 4. Now remember that this particular column is either 8 or 2. Those are the only allowed values that this particular column will be able to contain. That's why it's called the octet column. For hydrogen, it's the duet, since hydrogen can't contain 8. It can only contain 2. If you add this all up, this adds up to 20 electrons. In other words, if all these atoms over here were in a perfect environment, then there would be 8 valence electrons around carbon, 8 valence electrons around fluorine, and 2 valence electrons around hydrogen. I forgot to do this. There's actually 2 fluorine, so I gotta clear this and correct that. There's 2 times 8, that's 16. And let me correct this as well. It's basically simple math errors like that will throw you off. So 24 plus 4, that's 28. There's 28 electrons if each of these atoms in CH2F2 had a perfect octet. In reality, carbon has 4. So we take 1 times 4, and that's 4. In reality, fluorine has 7. So 2 times 7 is 14. And hydrogen has 1. 2 times 1 equals 2. So in reality, the total valence electrons for this particular chemical is 20. The magical thing about these two numbers is that if you take the octet electron and you subtract the total valence electron, that's the number of electrons used in bonding. And if you divide that by 2, you get the number of bonds. So this value right here is going to be 28 minus 20 equals, divide that by 2, 8 divided by 2, 4 bonds. But that was pretty obvious. If you look at this particular chemical, carbon is in the center, because generally the first atom in the formula is the center. And then fluorine flanks the carbon as well as the hydrogen. So the first thing that we need to do is we need to add the bonds. So there's 1 bond here, 2 bond here, 3 bond here, 4 bonds here. That takes care of 4 bonds. Now in terms of the valence electron, remember that we have 20 total valence electrons, and we've used a total of 8 in the bonds. 2 here, 2 here, 2 here, and 2 here. That's a total of 8. So when we subtract 8 from 20, what we end up with is 12. That's the number of electrons remaining that we haven't accounted for. If we take 12 and divide it by 2, that's the number of lone pairs. In this particular case, we have 6. So to complete this structure, what we need to remember is we need to apply the octet rule. And the octet rule simply says that atoms will have 8 electrons in its valence, except for hydrogen, which is satisfied with 2. So this fluorine right here already has 2. What it needs is 6 more. 1, 2, 3, 4, 5, 6. So if we have 12 and we subtract 6, that means we have 6 remaining, which is 3 lone pairs. And so that will go towards this fluorine right here. So what you have is a Lewis structure that looks like this. This would be your Lewis structure. Okay? If you take a look at this particular chemical, CHHF, F, and it's 3 lone pairs. The central atom is carbon. And if you look at the number of regions around carbon, that is the region of electron density, what we have is the following. We have 1 region, 2 region, 3 region, 4 region. So what we have is a center atom with 4 regions of electron density. And if you look at your VSEPR table, what you see here is 4 regions right here. 4 regions, so our electronic geometry is tetrahedral. And if you take a look at difluoromethane, then all these regions have bonded atoms at the end. So if we go back to our chart, we can see that we have a tetrahedral skeleton, but 4 bonded atoms at the end, no lone pair. Our geometry, molecular geometry, is tetrahedral. Its designation for the electronic geometry is AE4, and its molecular geometry is AB4, meaning that there are 4 atoms around the central atom. So we know that this particular chemical is tetrahedral. So that's what I'm going to put right here, tetrahedral. And its molecular geometry designation is AB4. So we're done with difluoromethane. Next thing I'm going to do is I'm going to do this chemical right here, ethane. Change pen. Ethane 1,2-diol. That particular chemical has a hydrogen, an oxygen, a carbon, an oxygen, and a hydrogen. So let's create our bond table again. HOCCOH. So we have 2 carbons, 2 oxygens, and 2 hydrogens. Actually, we don't have 2 hydrogens. We have a hydrogen here, and a hydrogen here, a hydrogen here, and a hydrogen here. So we have a total of 6 hydrogens. So let me correct that. So to work on this, again, we have the octet electrons and the total valence electrons. So remember that this column can only be 8 or 2, and it's only 2 for hydrogens. So 2 times 8 is 16. 2 times 8 is 16. 6 times 2 is 12. So we have a total of 32 plus 12 is 44. If all these atoms in this particular chemical were totally happy, then we would need 4 electrons to give each atom an octet and hydrogen a duet. But in reality, carbon only has 4. So 2 times 4 equals 8. Oxygen only has 6. 2 times 6 is 12. And hydrogen only has 1. 6 times 1 is 6. In reality, the total valence electrons that we have is 26. Now remember the number of bonds? That is equal to 44 minus 26 divided by 2. So that particular value is, I believe, 18 divided by 2. We have a total of 9 bonds. So let's go ahead and put this together. We have H, O, C, C, O, H. This is the atomic connectivity, and you don't have enough chemistry background to know this, and so we generally provide it for you, but that's the way the atoms are arranged. What we need to do is just connect them until we have 9 bonds. Remember that 1 bond equals 2 electrons. So for every line I write, that is equal to 2 dots. So that's 2 electrons, but that's 1 bond, 2 bonds, 3 bonds, 4 bonds, 5 bonds, 6 bonds, 7 bonds, 8 bonds, 9 bonds. So we've taken care of our 9 bonds. And in our 9 bonds, we've used 18 electrons. So the remaining electrons is going to be 26, which is your total valence electron. That comes from this right here. Change gears on you. Minus the number of electrons you've used in the bonds. That's 18. So that's a total of 8. And that's the remaining electrons. So the number of lone pairs is equal to 8 divided by 2. That's 4. So we're going to complete our Lewis structure by giving the atoms an octet. So if you take a look right here, this hydrogen already has 2. It's sharing with oxygen, but you can count each electrons between the 2 belonging to hydrogen and oxygen. So that hydrogen satisfied. In fact, all these hydrogens are satisfied. These carbons have 4 bonds. That represents 8. So these carbons are satisfied. The only elements that has not obeyed the octet rule are the oxygen. And what we have is 4 electrons around each oxygen. So we need to give it 4 more. Putting 4 on that takes away 4. So we still have 4 remaining electrons. After putting the first 4 here, the other 4 of course goes here. So this is your Lewis structure. So let me go ahead and draw that again. The Lewis structure that we have is hydrogen, carbon, carbon, oops, sorry. This happens to be oxygen, carbon, carbon, oxygen, hydrogen. Hydrogen's on the top and on the bottom. Hydrogen's on the top and to the bottom. We have 4 bonds. 1, 2, 3, 4. I mean, we have 9 bonds. That's our 9. We have 4 lone pairs. There's 2 on that side and 2 over here. So this is our Lewis structure. Now we need to look at the geometry. As it turns out, this particular chemical has 1, 2, 3, 4 central atoms. Since it has 4 central atoms, we have to figure out the geometry around each. And we can easily do that by just figuring out how many regions of electron density are around each particular atom. So I'm going to use a color pen here to kind of show you how many we have. So right here for this oxygen we have 1. Okay, we have 2, Lone pairs is its own region. We have 3, we have 4. That's one region. So this oxygen is going to be designated as AE4. Likewise, this oxygen over here will also be designated 1, 2, 3, 4. So this oxygen is also AE4. 4 regions of electron density around it. This carbon right here has 1, 2, 3, 4. So that is also AE4, as well as that because of symmetry. So our 4 atoms, our 4 central atoms, the first oxygen is AE4. Our second oxygen, it's to the right, is AE4. Our carbon is AE4, and our second carbon is AE4. And let me just remind you through the chart what I mean by AE4. We go over here, you can see that there are 4 regions of electron density around the central atom. And in our particular case, the carbons have 4 bonded atoms around it, whereas the oxygen only has 2 bonded atoms and 2 lone pairs. So let's go back to our structure. This particular carbon is going to be AB4 tetrahedral. This carbon is also AB4 tetrahedral. This 2 oxygen, however, is AB2E2. AB2E2. And the reason why they're AB2E2 is, let me try and show you this real quick. This oxygen has this lone pair right here. Sorry. This lone pair right here. There's a lone pair right there. These lone pair right here. This lone pair right here. So that's your E's. And then it's got these bonded atoms right here. Okay, it's got these bonded atoms right here. So that's your B. And yeah, that bonded atom is extended, but in relation to the oxygen, at the end of that bond, there's a bonded atom. That's why it's an AB2E2. Likewise with the other oxygen. Okay, so we've taken care of this particular chemical. We have 4 central atoms, and we know the geometry around each of the central atoms. This is a bent tetrahedral, and this too is a bent tetrahedral. Okay. Next, let's do our acetylene. Acetylene is going to be this chemical right here. It's also known as ethyne in organic chemistry. Let's do our bond table. It's got a hydrogen, a carbon, carbon, hydrogen. It's got 2 carbons and 2 hydrogens. So we want our octet electrons and we want our total valence electrons. Remember, this column can only be 8 or 2 for hydrogen, so it's 2 times 8 equals 16, 2 times 2 equals 4. So we have a total of 20 electrons. Again, that would be the number of electrons that you would need to give each atom in acetylene an octet, or in hydrogen's case a duet. So in reality, carbon has 4, so that's a total of 8. Hydrogen has 1, so that's a total of 2. And so we're stuck with 10 valence electron. The number of bonds is equal to 20 minus 10 over 2, or we have 10 over 2. That's 5. That happens to be 5 bonds. So let's draw our 5 bonds. We go ahead and put the atoms down in terms of how they're going to be arranged. And here you can see that there are 2 central atoms. I'll call this carbon 1 and carbon 2. Let's put in our 5 bonds. 1, 2, 3. And remember, hydrogen can't have more than 2 electrons, so you can't put another bond here. Otherwise, you would give hydrogen 4 electrons. That's not allowed. Where we need to put our other 2 bonds, because we've already used 3 from our 5, is between the carbon. Now if you count, this particular hydrogen has 2, this particular hydrogen has 2, this particular carbon has 8, 2, 4, 6, 8, and this particular carbon also has 8, 2, 4, 6, 8. So let me go ahead and erase those so that I have a clean picture. Okay, this is our structure. How many lone pairs do we have? Well, remember that we have 10 total valence electrons, and we use 10 in the bonds, so there are no lone pairs. We've taken care of all the electrons in this particular chemical, so there are no lone pairs. Let's take a look at the central atoms. This is a central atom and that is a central atom, and they're identical. There's 2 regions of electron density. Okay, 2 regions of electron density for each. So this is AE2 and this is AE2. At the end of each region, there's bonded atoms. There are no lone pairs, so it's AB2, AB2 as well. And again, if we look back in our VSEPR table, there's 2 regions of electron density right here. We're going to have a linear, it's an AE2 region, and there's 2 bonded atoms at the end of those regions. The molecular geometry is also linear right here. So we can finish this off and say that this particular chemical is the electronic geometry is linear, and the molecular geometry is linear. So it's basically just a linear chemical. Okay. Finally, let's do our last one. Our last is acetic acid. Acetic acid has a carbon and 3 hydrogens around it, and then it's attached to another carbon. It's got an oxygen, and a hydrogen. That's the arrangement for acetic acid. Okay. It's also known as ethanoic acid in organic chemistry. Eth for 2 carbons. Let's go ahead and do the bond table. And the bond table, of course, is CH3COOH. That's the structure. 2 carbons, 2 oxygens, and 4 hydrogens. So we'll do the octet electrons and the total valence electrons. Hopefully you guys already know this. It can only be 8 and 2. So 2 times 8 is 16. 2 times 8 is 16. Hydrogen can only be 2. 2 times 2, sorry. Let me redo that. That's 4 times 2 is 8. So in reality, what we have is 16 and 16 is 32 plus 8 is 40 electrons. So if each one of these atoms had the same number of electrons as the closest noble gas, then we would need 40 electrons. In reality, carbon has 4, there's 2 carbons, so that's a total of 8. Oxygen has 6, there's 2 oxygen, that's a total of 12. And hydrogen has 1, there's 4 hydrogens, and that's a total of 4. So if we add this all up, what we have is 24. So the number of bonds is equal to 40 minus 24. That's going to be a total of 16 divided by 2. That's going to be a total of 8. 8 bonds in the structure. Let's see. So, if that's the case, let me just double check here. 2 times 8 is 16. 16, that's 32, that's 40. This is 12 and 8, that's 24. So let's go ahead and put our 8 bonds. There's carbon, hydrogen, 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 carbon, oxygen, oxygen, hydrogen. That is the arrangement for acetic acid. I'm just going to move this down so I have space. And let's go ahead and put our 8 bonds. 1, 2, 3, 4, 5, 6, 7. And we need an 8th bond. And the only place that's logical, oxygen prefers 2 bonds. This oxygen already has 2. So it needs to go here. Plus this carbon was lacking 8 electrons. So that's how we put 8 bonds in this particular arrangement. Now the remaining electrons is going to be 24, which is our total valence electron, minus 16, which is the number of electrons used in bonds. Remember, there are 8 bonds, but there are 2 electrons per bond, so that's a total of 16. So that's going to be a total of 8. Remaining electrons, our lone pair, is going to be equal to 8 divided by 2. There's 4 lone pairs in this particular chemical. And the way we do that is we always go towards the outer edge and look for atoms that doesn't satisfy the octet rule. This oxygen right here, that doesn't satisfy the octet rule because it only has 4 electrons, 2 here and 2 here. So it needs 4 more. So from our 8, we use 4, we have 4 more. Of course, those 4 goes on this oxygen right here. So that is going to be our Lewis structure for acetic acid. Now let's take a look at the central atoms. Let's take a look at our electronic designation, and let me call that our AE system, and then let's take a look at our molecular designation, ABE system. So the first central atom, and there's 3 of them, is C1. C1's right there. If you look real closely, you will see that there are 4 regions of electron density. So that's going to be AE4. And if you look at each N, there's bonded atoms, so that's an AB4. We know right away that that particular compound is going to be, or that particular atom is going to be tetrahedral. So the electronic designation is tetrahedral, and the molecular designation is tetrahedral. And then let's take a look at our second central atom, that's carbon 2. And you can see here, change pen, we have 1 region, we have 2 regions, and we have 3 regions of electron density. So that's an AE3. In each one of these, and even though this is a double bond, it's counted as one region, there are 3 bonded atoms at the end, so it's AB3. So an AE3 designation is trigonal, and the molecular geometry would also be trigonal. So that would be the electronic and the molecular geometry. Finally, we're going to look at oxygen, and that's oxygen 3. That's this oxygen right here. Okay, so if we take a look around this particular oxygen, let me change pen. Let's see if I use blue. There's 1 region, there's 2 regions, there's 3 regions, lone pair counts as a region, and there's 4 regions. So that is a designation of AE4. And if we look at this particular chemical, there's an electron pair here, an electron pair here. So of the 4 regions of electron density, only 2 of them have bonded atoms at the end, and the other 2 remains as lone pairs. If we go back to our chart, that's this right here. Let me clear this real quick. Okay, we are right here. So our electronic geometry is tetrahedral. In one case, we had tetrahedral molecular geometry, but the oxygen here is going to be 2 bonded atoms, 2 lone pairs. It's going to be a bent tetrahedral, So, if we go over here, then we can finish this structure, and we can say that this right here is tetrahedral electronic geometry and bent tetrahedral molecular geometry. So we can go to our chart here and finish this. Total valence electrons for difluoromethane. Let's go back over here. That's a total of 20. 20 for that, 26 for the second, 10 for the third, and 24. So we have in this particular chart 20, 26, 10, and 24. Our Lewis structure for this is carbon, blow this up, fluorine, fluorine, hydrogen, hydrogen. Let me erase this. Let me put my lone pairs. For this next chemical, I have H, O, C, C, O, H, hydrogen, 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 and then the lone pairs are going to be right here. That would be my Lewis structure. This particular chemical would be this. H, C, triple bond C, H. And then finally our last chemical is this right here. And then our lone pairs are the following. So that pretty much takes care of the Lewis structure. The electronic geometry on this carbon is going to be AE4, that's tetrahedral. The atoms at the end don't have a geometry, it's only the central atom. So the molecular geometry is going to be AB4, and that is tetrahedral. Okay, for ethane 1,2-diol, we have our oxygens, and both oxygens have the same geometry, and we have our carbons. In terms of the oxygen, that's going to be an AE4, and our carbons also AE4. That means both of these are tetrahedral electronic geometry. In terms of the molecular geometry, the oxygens, both oxygens are going to be AB2, E2, and that's going to be bent tetrahedral. And then our carbon is AB4, and that's tetrahedral. Okay, so that's that particular molecular geometry. Our acetylene, both carbons are identical. The carbon will be designated as AE2, that's linear. The molecular designation for both carbons are going to be AB2, and that's going to be linear as well. And then finally, acetic acid, it has 3 central atoms, C1, C2, oops, sorry, yeah, where's that, C1, C2, and O1, that's our O1 right here. C1 is going to be AE4, it's tetrahedral. C2 is going to be AE3, that's trigonal. And our oxygen is going to be AE4, that's tetrahedral. Remember that this is the electronic geometry. The molecular geometry for C1 is going to be AB4. So around that particular carbon, it's tetrahedral. And then our second carbon is going to be AB3. So around that particular carbon, it's trigonal. And then finally, our last is oxygen. That's an AB2E2. That's a bent tetrahedral. So that pretty much takes care of this table. All we've got to do now is find the 3D structure. And you can do 3D structure if your instructor shows you by designating wedges and dash. So let me go ahead and pull that program, and you can see that in the computer. I'm going to change and the program that you want is called just do molecular modeling online. Let's go to Molview, and we're just going to close this. And then the other program that I want is ChemDL. ChemEd DL. Okay, so these are the two programs. One program will give us the rotating, but it's got to be in the library because you can't create models in this particular site. In the other one you can. So let's go to Molview. This is a structure of caffeine. What you can do here is, let me go ahead and clear this. What you can do is, of course, you can rotate the structure. Okay, so you can see the geometry around each atom. You just take your mouse and move your mouse. But let me go ahead and clear this so that I can explain to you the different features in this particular program. This right here, in organic chemistry, what happens is that if you draw a structure, okay, each end of the line and bend of the line represents a carbon. And then carbon always has 4 bonds. So if this carbon only has 1 bond towards one other carbon, it's implied there's 3 hydrogens in here. This carbon has 2 bonds to 2 other carbons, and so it's implied 2 hydrogens in here. So this particular structure that I drew is 1, 2, 3, 4, 5, 6, 7. 7 carbons long, and it's got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hydrogens. And if you want to see that, we can go ahead and clean up the structure. That's what the broom is for. And then take that 2-dimensional model and render it to a 3-dimensional structure. And here we have it. You notice that this is a zigzag formation. This, by the way, that I just drew is called the stick notation. This model on the right is called the ball and stick. And so you can see that we had 7 carbons, 1, 2, 3, 4, 5, 6, 7, and each hydrogen, the hydrogens are put in there automatically. And we do that in chemistry because we are lazy to write detailed structure. It requires the audience to know how to interpret these structure. So this right here happens to be heptane. That's the structure of heptane. Okay, so again, you can see that that's basically it. If I extend this, let me just draw a bunch of carbons coming out. I don't have to put in the carbons, it's implied, and then render that. You can see that that's exactly what's going on. Okay, I can just do one, and then here it is. Okay, remember that there are 1, 2, 3, 4, 5, 6, 7 carbons in this structure. Each carbon here has 2 bonds, so that means there are 2 hydrogens. I can do a cube like that and then get a 2-dimensional model. Okay, I can do a alternating double bond, which is our benzene ring, and do that. See now, this carbon has 1, 2, 3 bonds, so that means the 4th is a hydrogen. Belongs to this carbon, 1, 2, 3 bonds. The 4th is an implied hydrogen. Now, these features right here, the trash means to trash your structure. The erase means that I'm going to erase a bond, maybe. Let me do this. Okay, so let me go ahead and fix that. And let's say I want to remove one of this because I made a mistake, so I can erase it. And then I can replace maybe this with an oxygen, and then get the 2-dimensional structure like that. These are wedges and dash to give you some sort of 3-dimensional perspective. So if I put a line right here, and then I put a wedge here, and then a dash here, and then another line here, it tells me that I have basically a 3-dimensional. The wedge comes out of the plane of your screen. The dash means it's going behind the plane of the screen, and lines represents the same plane as the screen. So let me go ahead and render that. And that's what we have right here. Okay, you see how we have a this thing is called a tert-butyl group. This thing right here, it's called a tert-butyl group. So that's basically the templates that you have here. You can put electrons or you can remove electrons. So let's say that I put electrons right here, then that'll give it a charge. I can also remove electrons. say remove an electron here. Okay, so I can do that. And then, let me clear this. These are the different atoms. The more frequently used atoms are shown right here, and that's because this program is made for organic chemistry. And then if you want more elements, then you click on that and they'll give you the periodic table. So one of the chemicals that I made in graduate school had 2 iridiums and chlorine. Let's see if this works. And then see if I can't put a carbon in here. Actually, let's do a ring. And then I'll put a nitrogen in one of these. Okay, and another ring. And then a nitrogen on one of these. So this is a structure. Let's clean it up and then create the 3D model. Here it is right here. Okay, so that is how you would use this program, and it gives you a pretty good realistic view. I can change the different view to ball and stick, or just a stick, I mean. I can do a van der Waals radius, and that tells you the size of these things. I can do the wireframe, or I can do the lines. I can change the background here to gray. I can change it to white. Okay, I'll go ahead and go back to my ball and stick and then make the background black. That way I have some contrast. And then these other tools here, you could probably get some spectroscopy information. We'll try that in some of the compound that we have. So it's got some advanced features here. So let me go ahead and do our structure. Okay, I'm going to clean this up. The first chemical is difluoromethane. So it's got a carbon in the center, and then it's got fluorines attached to it, and then I'm not even going to do the hydrogens because hydrogens are always implied. I am going to connect these. Okay, you notice that sometimes the carbon is shown, sometimes the carbon isn't. I'm going to clean it up, and then I'm going to render it. So that right there is difluoromethane. I'm going to go ahead and cut and paste this so I can put it in my worksheet. So I'm going to give it a white background, and then I'm going to copy and paste. Okay, it's on my desktop. I'm going to go to ChemDL, and then I'm going to put in here difluoromethane. And it actually is in the library, and if I click on that, it'll find it. And here's the structure right here. I can rotate it with my mouse. I can make the molecule spin. I can do the van der Waals radius, which tells me the size of these things. I can actually do the bond length. Okay. I can also do the bond angle. And you can see that this is nearly almost a tetrahedral. 109.5, not quite. I can label the atoms for more complicated chemicals. Okay. I can do partial charges. Later on in Chem 200, you're going to learn about formal charges. That's what it is. I can turn off the labels. I can do molecular dipole, and that's what we want. We can see that this particular chemical is polar because it has a dipole moment. And I can also do the dipole for each bond. You can see that fluorine is more electronegative, so there's a dipole pointing towards the fluorine, a dipole pointing towards the fluorine. And so these are the other dipole. And then when you add up all those vectors, you get the molecular dipole. So I'm going to write 1.1719 in my sheet here. 1.1719 device. That'll be my chemical, and then I'm also going to put in here I'm going to paste it right in here. Unfortunately, I can't paste this structure into my iPad, but if it was in my computer, what I would do is I would just copy this and then paste it right in there, okay, for difluoromethane. So I'm just going to put it on the side here, out of the way. Let's do the next one. The next one is, let's clear this up. Remember, it's ethane 1,2-diol, and so this particular chemical has 2 carbons, an OH on both sides, and then I'm not even going to draw the hydrogens. It'll be placed in there automatically. And then I'm going to go ahead and render this, or clean it up first. And then I'm going to go ahead and create the 3-dimensional structure. So here it is right here. I'm going to go ahead and copy and paste. Then I'm going to see what the space filling model looks like. Here it is right here. I'm going to explore maybe some of the properties that this thing has, like the spectroscopy. Oh, no spectrum. Okay, let's go back. Anyway, I was just seeing if that thing works. So that right there is ethane 1,2-diol. Let's go and put it right here. In this particular case, I'm going to write C2H6O2. And I'm not going to write the name. I'll just put the formula, and here it is right here. And here's the structure. And I'm going to look at the dipole. And this particular chemical is polar. You can see right here that it is polar. And the dipole moment's 2.481. So that's what I'm going to write in my chart. 2.481. 2.481. Device. That means that if they have a dipole, that means they're polar. Okay. I'm going to do acetylene. So I'm going to clear this right here. There's 2 carbons, and there's a triple bond in between. You got to put the triple bond, because if you don't, it's going to imply that there are going to be 6 hydrogens on this thing. So that's acetylene ethyne. I'm going to go ahead and clean that up, and then I'm going to do the file. Here it is right here. Okay, it's linear, just like we predicted it would be. It would be linear. Copy and paste. And let's use ChemDL to figure out what the so it's C2H2, and what we have here is C2H2. It's not shown here. Maybe I put in acetylene. Here it is, right? No. C2H2. It looks like that particular chemical isn't in this library. Oh, here it is. It's better known as ethine. Here it is right here. Okay, it's linear. And let's look at the dipole. It's got 0 dipole, as expected. So we're going to put here 0 dibis. This is nonpolar. And finally, we're going to do acetic acid. So let's do this. Let's go over here. I'm going to clean this up. Acetic acid has carbon, carbon, oxygen, oxygen. Remember that hydrogens are implied. I am going to connect these. Yeah. Erase that. That was an error. And I'm just going to put the double bond right there. And I actually need to show that it's a double bond. And you can see that that's the structure I have. But when I clean it up, it does that. That right there is acetic acid. And if we do the three-dimensional structure, we have this, and that's acetic acid. So I'm going to copy and paste this structure into my notes. You can see it's tetrahedral on the carbon, it's trigonoplanar on the second carbon, and it's bent on that oxygen, just like we predicted. Okay, it's bent on that oxygen because there are lone pairs on this oxygen. When you do the model, it doesn't show the lone pairs. Let's go ahead and put acetic acid up here. And you probably already know that acetic acid is polar. Here it is. And we can go here and figure out what the dipole is. The dipole for this guy is only 1.5783 dBs. That's the unit. 1.5783. Okay, so that is our information. All I've got to do is paste the structure in here, and I already have the geometric designation here, and so I'm pretty much done with this particular activity. So that is how you would complete this worksheet. Now in your worksheet you do have some unknowns, and you would work on the unknowns in a similar fashion. Alright, thank you very much for listening, and hopefully you learn some of the tools that you can use in chemistry in the internet.